Nuclear half-life. A macroscopic, which means large, sample of any radioactive substance consists of a great number of nuclei. They do not all decay at the same time. The decay is random, and the decay of one nucleus has nothing to do with the decay of any other nuclei. Now, the number of decays during a specific time period, is proportional to the number of nuclei as well as how long of a time period you've chosen. Mathematically, I'm not sure you've all had this yet, but exponents, it's defined as an exponential decay. And that means, for example, if I have a graph like this and I start out with so many nuclei, it decays very fast in the beginning and then kind of tapers off like that. That's an exponential decay. After each specific time period, half of the nuclei decay. And it only seems to make sense to call that a half-life, okay? So the specific time period where half of the radioactive nuclei decay into something else is called that isotope's half-life. The isotopes of a specific element have very different half-lives. Some isotopes never decay and some will decay in microseconds. So just by changing the neutron number, you've totally changed the nuclear properties of that element. The half-life of an isotope, let's underline half-life again, is defined as the amount of time it takes for half of the original amount of the isotope to decay. Let's take an example. We have 200 grams of an isotope and its half-life is 2 years. We want to find out how much is left after 6 years. So what we're going to do is after one half-life, after 2 years, you're going to lose half of the 200 grams. So you'll be down to 100 grams. Okay? So you start with that for your next half-life. 2 more years, which will be a total of 4 years from the beginning, which is 2 half-lives, you're down to 50 grams. I wait another 2 years. Now this here, this 2, 4, 6, this is cumulative. This is 2 years from the beginning, 4 years from the beginning, 6 years from the beginning. So now, after 6 years, which is 3 half-lives, I take this 50 grams, cut it in half, and I'm left with 25. So, the answer is, after 6 years, 3 half-lives have gone by. Each time you cut this in half. So it went from 200 to 100 to 50 to 25, and you have 25 grams left of this radioactive isotope. And if you were to plot it on an axis, where up here you started at 200 grams, it would follow an exponentially decaying curve like that. Another way of solving this and getting closer to an exponential notation is to recognize that a time interval of 6 years, now this is the same problem we just did, where you had a half-life of 2 years, 6 years is going to give you 3 half-life periods of 2 years each. 3 times 2 is 6. So n will be the number of half-lives, which in this case is 3. X is your original sample size, how many grams of the material you started out with. And y will be what you have after 3 half-lives. Now here's where we get into the math. The 2, here let's look at this right here. This is the equation we'll be using. The 2 represents each time you have a half-life, the sample size gets cut in half. So y, which is your final amount of material, is equal to x, the original, divided by 2 raised to the n power. So I plug in the numbers here. I have 200 grams, 2 raised to the 3rd power, which is 8. 200 divided by 8, 25 grams. A certain isotope has a half-life of 12 minutes. If the sample size is 60 grams initially, how long will it take to decay to 7.5 grams? Calculate the factor by which the sample has decayed. Here it's 8. What you do is you have 60 grams in the beginning and you have 7.5 at the end. You divide those two and you get the number 8. Now, the power of 2 is the number of half-lives elapsed. So you try and find out 2 to what power gives you 8. Well, let's see. 2 times 2 times 2. That's good. So that's 3 half-lives. Then multiply the number of half-lives by the half-life, which is 12 minutes, and you get the total time to equal 36 minutes to decay to 7.5 grams. There's another way to do this, and that'll be on the next slide. We're avoiding exponents in this solution, and the way we're going to do it here is create a chart with the elapsed time and amount of the isotope. So begin with time 0 and increase the time by increments of the half-life. So the half-life is 12 minutes, so you go 12, 24, 36, see how they're multiples of 12, and then etc. Then fill in the amount of our isotope and decrease it by half each row because we're dealing with a half-life. So at time 0 we have 60 grams. After one half-life of 12 minutes, we have 30 grams. It gets cut in half. The amount's cut in half. 2 half-lives, or 24 minutes, cuts in half again. You get 15. Cut it in half one more time, and you get 7.5, which is what the problem asked. So it takes us 36 minutes for the sample to decay to 7.5 grams, and that's in 3 half-lives. A certain isotope has a half-life of 2 hours. If the sample size is initially 50 grams, how much will remain after 8 hours pass? First, divide the total time by half-life time to calculate the number of half-lives elapsed. So we have 8 hours divided by 2 hours, and you get 4 half-lives. Now we have a little equation here. Divide the initial mass, which is 50 grams, by 2 raised to the number of half-lives power to calculate the final mass. So that's 50 divided by 2, and there's the number of half-lives right there. So 50 divided by 16, 3.125 grams. To avoid exponents, create a chart with the elapsed time and amount of the isotope. Once again, begin with time 0, and then our half-life is what, 2 hours? So go 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. Then fill in the amount of our isotope at each time. Decrease it by half each time you go down one row. Start with 50 grams. At 1 half-life of 2 hours, you're down to 25. Next half-life cuts it to 12.5, then 6.25, and finally, at 8 hours, we have 3.125 grams. So after 8 hours, we have 3.125 grams of the isotope remaining.